Hello students, in the last video I have covered the fundamental of capacitance, what is a capacitor and how do we increase the capacitance of a conductor by introducing another conductor near to it and making a capacitor. And we have briefly covered the capacitance of the parallel plate capacitor. However, in this short video, I will once again cover the parallel plate capacitors, the spherical and the cylindrical capacitors, and what is the capacitance of these capacitors. As you all know that the capacitance depend upon the shape and size of the capacitor also. So the first one is a parallel plate capacitor. You can see here in this example, we have put two parallel plates are there. The area of each plate is A. The separation between them is given as D. The charge density sigma is given by Q by A, and V is the potential difference between the plates. And you know the relation between the electrical field, electric field, and the potential is given by V is equal to E dot dr. This is a very important relationship. So by using the Gauss's law, there is a separate video on Gauss's law. You can refer to that. Here I have taken a plate through which there is a Gaussian surface, cylindrical surface is made. So the two ends will have E and area vector which will have the same direction. So there is a 0 degree. So the angle between E and area vector is 0 degree, whereas on the spherical surface the area vector is 90 degree to E, but cos 90 degree is 0. So circular surface is not going to contribute to the electrical flux, and only the two end surfaces are going to have an effect on the electrical flux. So by using the Gauss's law, E dot dA q upon epsilon is equal to q upon epsilon naught. Q, I will keep on repeating, it is an enclosed charge between the in the hypothetical surface, and this round is that we are always taking into account the closed surfaces. So 2 times of E delta A, that is for end surfaces, and for one curved surfaces is q upon epsilon naught. As I told, that angle is 90 degree for curved surface, so it is not going to contribute, and it is 2 E delta A cos 0 degree is q upon epsilon naught. By expanding, through which I get 2 E delta A is q upon epsilon naught, but q is nothing but the charge, which I can write as sigma into delta A. Delta A gets cancelled, so I get an electric field because of a thin plate which is having a charge density is given by sigma upon 2 epsilon naught. Since there are two plates, therefore the negative plate will also contribute to the electric field, which is also in the same direction. You can see here, which will also be in the same direction. So the total electric field, because of in between the two plates, because of the two conductors, will be sigma upon epsilon naught. So the first thing is, by using the Gauss's law, we find out the electric field between the opposite conductors between the opposite conductors. So the electric field, once we have found out, then we use the relation between V and E, which already you know, V is equal to minus integral infinity to R E dot dr. Now by using this, and between E and dr, as we are moving from the negative plate to the positive plate, and electric field is from positive to the negative, so there is a 180 degree difference between them. So 180 degree and minus, they will cancel out and it will become 0 to d E dr. So V is equal to E times of d, through which I can find out the electric field, which is V by d. So there are two ways by which I can find out the electric field. One is with the charge density, and by knowing the potential I can find out the electric field between the two conductors of a capacitor. So now I am equating both these electric fields together, and sigma is q upon epsilon naught a v by d. So I will get q by v, which is epsilon naught a by d. But you must have seen in my previous video also, capacitance is nothing but charge stored by charge to increase the potential by unit volt. So C is equal to Q upon V. So C is equal to, I can say Q upon V is nothing but epsilon naught A by D. So this is the capacitance of a parallel plate capacitor. Now the second example we will cover for the cylindrical capacitor. Here in this you see there is a cylindrical capacitor. The positive cylinder with the red one is outer cylinder and the inner one with the negative cylinder with the yellow color. And I have made an hypothetical surface, Gaussian surface with the dotted blue lines. So the total charge is lambda into L and the charge per unit length is lambda and the length of the capacitor is L. As you can see here, the electric field is going inward. The electric field is going inward. Therefore, E and dr, you can see E and dA will have the same direction, and the end surfaces, what is happening that E electric field, you can see here that electric field is going like this and dA is like this. So there is an angle of 90 degree between them. So ends are not going to contribute to the electric flux. So E into 2 pi RL is Q upon epsilon naught. So E is equal to Q upon 2 pi RL into epsilon naught. This I have substituted the value, and this is nothing but lambda upon 2 pi epsilon naught R, because Q by L is lambda. Lambda is Q by L. You can see here. So electric field is given by the Gauss's law by lambda upon 2 pi epsilon naught into R. Now by using the relation of potential, electric potential and the electric field, again if I am using that and putting the value of E which we have obtained from the Gauss's law between A to B lambda upon 2 pi epsilon naught R into dr, here you can see that we are going in the outward direction from A to B, and electric field is inside. So there is a difference of, there is an angle of 180 degree. So 180 degree means minus sign cancels out and this will become A to B EdR. So I have substituted the value of lambda E which I got from the Gauss's law lambda upon 2 pi epsilon naught R dr, and then we have solved it by using the integration. So it is 1 by R, integral 1 by R dr, which is nothing but log of R to the base E. So A to B. So A to B, it is limits is from A to B. So we have solved this and then we have substituted the value of lambda as Q by L, and then Q by V is nothing but capacitance. We know from the definition of capacitance, and we get the value of cylindrical capacitor as 2 pi epsilon naught L divided by ln of B by A. So this is another example. We will come to the spherical capacitor. The spherical capacitor, same thing. We have an outer sphere with a positive charge, inner sphere with a negative charge. There is a hypothetical surface. We have used the Gauss's law to find out the electric field in between these two conductors, with a positive and negative charge. So it is nothing but 1 upon 4 pi epsilon naught Q by R square. I need not to explain much because ds of the whole sphere will be nothing but 4 pi R square. Okay. So it is electric field we have got. Now V is equal to minus E dot dr, again using the relation of potential, electric potential and electric field, and angle is 180 degree because we are moving outward and electric field is inward. So there is an angle of 180 degree. So this value is substituted 1 by R square dr, and by using the integration we have solved it and found out the value of value of spherical capacitor. So this is Q upon V is 4 pi epsilon naught into AB upon B minus A. Hope by using the mathematics and the fundamentals of physics, you can now find out the capacitance of the various capacitors. Now the idea to explain shortly about this is, there are two steps involved in this which you must understand because there may be questions of different types. Now we are first using the Gauss's law to find out the electric field in between the two conductors. Once we have found out the electric field, then we have used the relation of electric potential and electric field to equate electric field and find out the capacitance. So these are the two steps which we have to follow for any question, for solving of any question. So fundamentally these are the steps involved. So my idea was to explain this, that I have fundamentally used these steps to solve or to find out the capacitance of the capacitor of different shapes. To understand this, I will I have taken one more example. Here it's a parallel plate capacitor. In between I have introduced a conductor which is having a thickness, conducting plate which is having a thickness T. So when I introduced this, what is happening? Electric field inside the conductor becomes 0, outside it is sigma upon epsilon naught. So your equation, the relation between V and E becomes E times of D minus T, because E in between the T is 0. So V will become E times of D minus T by using the same formula. And we know E is equal to sigma upon epsilon naught from the Gauss's law. So we have equated this and easily found out the capacitance in this case when we have introduced a conducting plate of thickness T in between the parallel plate capacitor. So this is the fundamental we have to always use to find out the capacitance of various capacitors. Now in the next video we will cover dielectrics and the capacitors in series and parallel and the storage of electrical energy in the capacitor. Hope you would have understood the basic concept of this video, which mostly covers these two steps. You need to understand these two steps. The motive of this video is to explain that we have to follow these two steps to find out the capacitance. So we hope you would have understood. We will come with the next video very soon.